First of all, thank you for having me join your meetup here. I turned my video on. Hopefully you can see me. It's a little bit hard over virtual. You know, everybody's virtual now. One day I would like to come out and see your country and present live. And so I think you were interested in having me speak about Istio and service mesh in general. And so that's going to be the topic for today. And I think you did an introduction for me, so I appreciate it. I'm the field CTO here at Solo. I've been involved in open source and helping organizations build large distributed systems, services, architectures, microservices, and so on. I do write a lot about this on my blog. I share interesting things on Twitter, and of course, I am writing Istio in action right now. So some of the content that we go over will be, you know, also presented in my book. Oh, wrong way. So I came to Solo maybe 2 years ago because I saw this transformation happening in the cloud native ecosystem and how it would disrupt existing ways of connecting our applications. And so service mesh is part of that story. And really this is a level 7 networking story, an application networking story. How do we get applications that need to communicate with each other and share APIs, and maybe they're distributed across multiple clusters on cloud native infrastructure, maybe like Kubernetes, likely across multiple deployment footprints, meaning on premises or in a cloud, and geographically distributed, and so on. How do we solve the problem of getting those applications to talk to each other and do that in a secure way, and do that in a way that we can manage it? Because the bigger these deployments and the more microservices that you're deploying and so on, it gets complicated pretty quickly. And from the application perspective and the networking perspective, how can we solve some of those problems? And so that's what we're doing at Solo. And we're taking some of this innovative technology like Envoy proxy and Istio and service mesh, or rather Webassembly and so on. And we're making this applicable and consumable in organizations that are looking to adopt technology to drive their organization or modernize their existing technology investments. And so specifically what we're doing at Solo is we have products organized around securing traffic at the edge of a boundary, let's say a cluster, a organizational unit, a data center, whatever. And so we built something called Glue Gateway to help solve that. Glue is built on Envoy proxy that solves things around application security, such as OpenID Connect or OAuth flows, web application firewalling, open policy agent authorizations, and so on. And then once you get traffic into your boundary, you need to secure it east-west directional and get telemetry about it, understand what's happening on the network. And so that's where Istio or service mesh comes into play. And we have enterprise support for Istio. And then the last part of the puzzle is once you take this boundary or this east-west traffic and scale it out across multiple clusters, multiple deployment targets, availability zones, geographic regions, and so on, that becomes very difficult to manage. And that's where we built a product called Service Mesh Hub to manage these multi-cluster and multi-mesh deployments. Now, the interesting part about adoption of these types of technologies is in how do people customize it to fit their needs? No organization is exactly the same as another organization. And that's where WebAssembly comes into the picture. WebAssembly is a way to extend the capabilities of a data plane or a control plane to fit the needs of the organization and run that in a safe, secure way inside of one of these Envoy proxies or inside of one of these data planes. So I can I can come back at any point to talk about these technologies. Here's a sort of a picture of what this might look like deployed across heterogeneous infrastructure and what the gateway and service mesh integration might look like. So let's get going, right? So we're talking about microservices, we're talking about cloud native infrastructure, maybe deploying to Kubernetes. This is a big assumption change from how we deployed our applications previous to this, right? Where in the past we might say, well, we'll deploy it on these VMs, or this infrastructure is more static, right? We know that this VM has an IP address. We write our firewall rules around these IP addresses. We know that the database lives on these VMs, and the database will never go down. The network will never go down. We have redundancy, and our applications we end up building our applications with these assumptions, and the reality when it sets in shows that this is not the case, right? These VMs can go down at any point. The network is not reliable. But when we start to adopt Kubernetes and cloud-based infrastructures, things that are more ephemeral, so there's no guarantee that they'll be around, things that are much more elastic, so they could be scaling up or scaling down, or the applications could become unhealthy for any reason, we have to change our assumptions. And one of the biggest assumptions that we have to revise is this idea that the network is resilient, or that the network is reliable, right? And so this is not a new concept, but it becomes even more, it becomes worse in this environment where we've now gone from a handful of large systems to many hundreds or thousands of small systems that now communicate over these cloud networks, right? So as we start to go to things like microservices, deploying into cloud infrastructure, we move a lot of the complexity of running and operating a architecture like that between the services, so onto the network. And now when an application A tries to talk to application B, it's not as simple as just opening up the port and sending the bytes through. Even that is precarious, right? We see that the network is not a straight line between A and B. But now there are things like service discovery. Where is service B running? And if it's scaling, auto scaling, deployed on multiple clusters and so on, how do we find those services? And when they start to fail, how do we know which ones to avoid, right? So we need some kind of smart client-side load balancing. We need things like timeouts and retrying and circuit breaking. We need now more control over how the traffic gets routed. In a monolith where you're making calls in memory, that control is sort of all in one. But now when you have microservices that are being deployed at independent rates, they're changing, we need to be able to control the routing between the services. We need to do things like canary releasing. We need to do things like traffic shadowing, so we can introduce new versions of a service and take shadowed traffic, mirrored traffic, instead of live production traffic, to reduce the blast radius of making these changes. And we've got to do things like health checking and telemetry collecting logs and stats, and trying to make sense of it, right? Because the more information that we can get, and it's not that easy to get it, but once we get it, we need to somehow make sense of it and use that to drive down our mean time to recovery, keep down the number of defects that we introduce into production, and so on, right? Now, the interesting part about this problem is that it's not entirely new, right? We've seen in the past things like enterprise service bus or message queues, or more recently, maybe API gateways, as kind of a partial solution to this problem, though in a more static environment, as I mentioned before things like Kubernetes and containers and so on. And what we saw the previous generation of cloud companies do is solve this problem in a highly decentralized way, right? So they didn't put big API management appliances in the middle of their architecture and force everything through this black box and bottleneck and so on, right? They distributed out how they solved this problem. So you may have seen technology like Netflix OSS, or Twitter came up with a framework called Finagle. Basically, they put the logic of timeout, retry, circuit breaking, load balancing, service discovery, and so forth into application libraries. And they forced the developers to use these libraries in their code. Now, this worked fine, but the problem now becomes when you have more than one language that you're trying to support, or more than one framework for any one particular language that you're trying to support, building libraries that implement all of this functionality that I just covered in the previous slides, and keeping that up to date and keeping that consistent between the different implementations. So for example, in Java, maybe you're using Spring, and maybe you're using, in a different language, you're using some reactive framework. In a different one, you're using Node.js or Python. Trying to implement circuit breaking, timeout, retry, load balancing, service discovery, tracing, telemetry collection, all this stuff, exactly the same across all of the languages is a monumental effort. It's a huge investment. And then trying to keep it up to date with security patches, with bug fixes, and trying to coordinate and roll out so that everybody has the same version and so on, is impossible, I would say, in these large enterprises. And then you don't want to get into a situation where you have incomplete and inconsistent implementation of how you solve these problems on the network. Then you have no way of reasoning about how things are failing or why they're failing or how to debug them, because every language is different, every framework is implemented differently. All right, so these networking challenges for our applications is where the service mesh sort of fits in as a solution to help solve that. So the first step in the service mesh solution is, if you have lots of applications, lots of different languages, or let's say more than one language, more than one framework, and you need to solve these networking problems. These are not optional to solve. If you don't solve them, you're going to end up with catastrophic failures, cascading failures, and so on. The first step in the service mesh pattern is then to say, let's implement those capabilities, the timeouts, retries, circuit breaking, these types of things, in a way that is transparent to the application. It's not Java specific or Node.js specific or Python specific or even Kubernetes specific. So what we could do is abstract away those capabilities and run them as though they're part of the application, but they're out of process from the application. So now when we deploy a JVM, we also deploy a little proxy that implements this behavior. When we deploy a Node.js process, we also deploy a little proxy right next to the Node.js process. Right? And so in Kubernetes, you can think this model makes quite a bit of sense, right? Because in Kubernetes you have pods, and those are deployed atomically, and this proxy ends up becoming part of the application. You can think of it as sort of an interceptor for the application. In our programming languages, we're all familiar with interceptors, right? If we're making network calls, we just add some filters and interceptors, and then we change some of the characteristics of the call. That's exactly what we're doing with this proxy, except this interceptor lives outside of the application. So it's no different. And inside of this proxy, we can implement things like routing control, like service discovery, load balancing, timeouts, retries, circuit breaking, telemetry collection, and so on. And now if all of the applications in our network have this smart proxy, regardless of what language they're written in, you can be sure that the implementation of these features is consistent. Right? It's called coming from the same code base. And now once you deploy this out into a fleet of services where each one has a proxy, now you need some way to control it and to configure it and to set policies and so forth. When traffic goes from the app to another app, it goes through these proxies. First, the local one, and then on the other side, when it gets to the other app, it goes to the remote one. And now you can do things like automatically upgrading this transport, this connection to TLS or mutual TLS. Right? I don't know if it's Java developers. I came from a Java developer background, but the other languages are similar. Setting up key stores and trust stores and ciphers and all of this stuff for Java applications is such a pain in the ass, right? And if you can just abstract that away and just put that on the network, then you allow the developers to focus more on their business logic and their code and not this networking stuff that has to live on top of it. It has to live on top of it, right? You can't ignore that. So with this model, we can do things like collect telemetry consistently. We can provide for things like distributed tracing. We can automatically upgrade the connections to mutual TLS and have secure traffic between all of our services. We can write policies about what services are allowed to talk with which other services. All right, so this idea of putting these little agents or these little interceptors with every single application gives us a lot of control, programmatic control now over the network. So a service mesh ends up being consistent of the proxies that live with the application, which we call the data plane, and the control plane components that drive the configuration of the data plane. And the control plane is actually what the users, the operators, the SREs, automation tool, and so forth, that's what they use to drive the behavior of the network. So generally, we can say that a service mesh provides this type of capabilities to the applications: service discovery and load balancing on the client side, secure end-to-end identity verification and encryption of the traffic control, traffic shifting and shaping, and so on, so that when you deploy new versions of an application, you can be very fine-grained about how traffic arrives at that new version, no matter where it is in a call graph. It doesn't have to be just at the edge like you can do with typical gateways. It can be multiple hops into a call graph. We can also collect telemetry, like I said, implement things like circuit breaking and so on, and do this from the direction of an API. Like I said, the control plane is driving the behavior. The control plane provides an API, and now you can automate your network on top of that. So that's where Istio comes into the picture. Istio is an open source implementation of a service mesh. Now, it's not the only one. There are other ones. But in my experience working in the field and my participation in the ecosystem and the community over the last more than 3 years, Istio has become the sort of de facto open source service mesh choice that people are going with right now. Now, like I said, CNCF has other options. Istio is not part of CNCF. Each cloud vendor has their own service mesh, but from a self-managed on-prem or just you need control over the mesh perspective, Istio is the most dominant one that I've seen so far. So why don't I give you a quick introduction to Istio? And I prefer to do that using a mechanism that you, when you leave this meeting, can also use, right? So I explained the basics generically of what a service mesh might look like. But what might be interesting to you is when you go to the Istio documentation, you can read a little bit more about how Istio implements and does some of these things specifically. So if you click on concepts and what is Istio, it goes over what is a service mesh and some of that stuff. But it will explain exactly how Istio works in terms of it deploys a proxy next to each application. And that proxy is a technology called Envoy proxy. Envoy is part of the CNCF and also happens to be one of the foundational pieces to building this type of technology, whether it's gateways at the edge, like we do at Solo with Glue, or whether it's other service mesh implementations. So Envoy is fundamental here. And then you can go into setup and some of the examples and so on. Why don't I give you a quick rundown? So let's take a look here. I think we have a fresh cluster here. Yes, we do. And so I have Istio downloaded, and I actually have the 1.7.2 version. You can download it yourself at GitHub Istio/Istio, right? And under releases. 1.7 is the most recent. 1.8 should be coming out in 2 weeks. And then 1.6 is the previous release. So what we want to do here is we're just going to install the service mesh. There's different profiles that you can pick from, minimal, advanced, demo, and so on. We're just going to go with the default one. And then let's take a look at what it installs. What we expect here, let's come down here, and we should see, we use a Kubernetes dashboard to watch our Kubernetes cluster here. Let's look at the namespaces. We see that an Istio system namespace is being created. If we look in there, we see a couple, well, we see this one container coming up, and we see another one coming up. And the components that are being initialized right now are the components that will make up the control plane. So I mentioned this idea of the data plane and control plane. Right now we're setting up the control plane. And so it looks like that has come up. The next thing that we want to do is we want to, so here, let me just see if I can, let me just give you a little bit more. These are some of the diagrams that I used in my book. So basically the Istio D, or this control plane controller, will eventually be talking to some of the application proxies. Right, these sidecar service proxies, we call them. The Istio control plane will also be reading API objects from Kubernetes in this case, because that's where we're going to use these blobs of YAML to drive the behavior of the service mesh. So let's take a look at that. Why don't we install a very simple sample application? So that would be in here. It's actually one of the ones that comes with the Istio distribution itself. So if we apply this into the default namespace, and we come back here, let's go to default, let's take a look. We see we have our HTTP bin service coming up and running. Now the first thing we notice is that we see, hopefully eventually when it comes up, that we'll have one container running in this service. All right, so we just deployed this to Kubernetes. Now if we want to make this part of the service mesh and make it Istio aware and upgrade its abilities to do things like timeouts, retry, circuit breaking, distributed tracing, that kind of stuff, what we need to do is add that sidecar proxy to this deployment. Now there's two ways to do that. One is to do it manually. Right, so instead of kube apply, maybe I do Istio cuddle kube inject. And if I take a look at what this gives me the same deployment that we deployed to Kubernetes, but it enriches it or adds the service proxy. So if we come down here, we start to see the configuration here for the service proxy. Now, if we scroll down far enough, we might find that here's the actual container image for that proxy. Now we could manually apply this. There's also a way to automatically inject this. So why don't we kubectl apply. Why don't apply? Why don't we manually do it right now, and in another demo we'll do it automatically. But now you can start to see down here that we've got two containers running with our HTTP bin service. Now to the HTTP bin service, nothing changed in the application. The proxy is running transparently to the application. When traffic goes into the application, it first goes through the proxy, through the service proxy. When traffic leaves the application, it first goes through the proxy, right? And so now we can enable it with these additional capabilities. So from here, let me show you a demo of this kind of all working together. Demo, let's do this one. Oh. Let's do this one. All right, so we didn't set it up. Let's set up the demo here. And while we're setting this up, go back here real quick. We should see in our Istio demo resilience namespace, we should see three deployments that have come up. They were injected. The sidecar injector did this automatically, so we set this up to do sidecar injection. The only requirement for doing that is to label the. So if we take a look at the resilience namespace, is really just to label the namespace with Istio injection label, and then whenever we do a deployment, Istio will automatically, using a webhook, will automatically inject the sidecar there, so we don't have to do it manually. Now let's take a look at the demo. So the first thing that we do, we have three different services. The web API is sort of the front end. That's what gets called first. So when I send traffic into the cluster, it'll go to this service first, and then it will go to the recommendation service. And as part of making recommendations, it will reach out to a service called purchase history, right? So web to recommendation to purchase history is the chain or the graph of calls that we'll see here. So the first thing to notice is that on the bottom pane here, if we can get this, we have a loop that's just going through, and it's calling the cluster, and it's going through an ingress gateway, but it's going to the cluster, and then it's going to the web application. So if I stop this for a second, we can see the traffic comes into web. Web then says hello, but then also calls recommendation. And then recommendation says hello, and then calls purchase history, in this case, version 1. Right, and so then we see the response from v1, HTTP 200, everything is good. If I can let it continue, you should see that this is a loop. The calls are continuing. So let's say we want to deploy a new version of the purchase history service. And why this is interesting is because this is 3 hops into the cluster, right? We got the hop into the gateway, the hop to the web API, the hop to recommendation, and then to purchase history. So let's deploy this. So this is the YAML, right? We should see a message of v2 when that gets deployed. So why don't we create it and let it get automatically injected. See that, and then I think if we get the pods here, we should see it is coming up, and indeed it does have the Istio sidecar injected, so that's good. On the bottom here, we see the traffic is still going to v1, and this is by design. So instead of letting Kubernetes load balance automatically between the different versions, which it would otherwise do, if you set up a service with matching selector and label and that kind of stuff, you would see that the traffic is load balanced. The difference between what Kubernetes load balancing is doing and what Istio's load balancing is doing is that Kubernetes just sees connections. Kubernetes sees a connection come in and says, hey, I want to talk to this IP. And Kubernetes then says, okay, well, we got 3 of these pods, load balance across the 3 pods, the connection. Istio has a much finer grain visibility of how to do the load balancing. Istio sees the actual requests, right? So we're talking about L7 level. Istio sees the request and says, oh, this request should be load balanced like this, or this request should be routed to a different version like this, which is not, so while Kubernetes is doing TCP connection load balancing in a very simplistic way, Istio gives you much more control over both the connection load balancing as well as the request level load balancing. And in this case, we see we're forcing all the traffic using Istio to V1 of the purchase history. Now, let's say we want to take a, I think that should be okay. Let's keep going. So again, this is a live demo. I do have this script typing for me, but this is a live demo. Let's see if I cross our fingers. We don't have it working. Let me see 1 second. UCTL. Let's go CD. Resilience demo. To the all. Let's try this. All right, and then let's try this one again. Now we should see something. Let's watch this down here. Okay, so we see V1 is getting traffic, and then V2 is getting some traffic. So let's take a look at what exactly that is. First of all, we started with this. We said we used Istio's API that we give to the control plane, right? This is the API that says, when we call purchase history, send 100% of purchase history requests to version 1. And then we said, let's start a canary release and send 10% of the traffic to version 2, while 90% goes to version 1. So we should see that behavior here. It changed approximately 10% of the time. The traffic will go to V2. Now let's say, okay, that's all good. Traffic looks good. The logs look good. Statistics look good. Let's continue. Let's roll out 50% of the traffic to V2 of purchase history. And now we should see approximately 50% of the time that traffic is load balanced between V1 and V2. Now, lastly, let's say, fine, that looks good. Let's roll everything to V2, or roll 100% of the traffic to V2. And now you should see all of the traffic going to V2. None of it is going to V1. And again, the fidelity of the routing that we have and the control that we have here is not just the connection level, but at the request level. And we can give very fine-grained control over how requests end up getting routed in this network. Now, let's see, how much time do I have? About 5 minutes. Let's do one more thing. Let's do a retry demo. Let's put all the traffic back to version 1. And we see that has occurred now. What we're going to do is we're going to disable, so Istio has automatic retries under the covers by default. So if there are network errors, 503s, 504s, these types of things, Istio is automatically configured to retry. I'm going to disable it for a second because I want to show you exactly how it's working and what's going on. What we're going to do is we're going to deploy version 1 of the purchase history service with a version that responds 50% of the time. It will respond with an error. So as you can see now, maybe we did a bad deployment somehow, and we've created a situation where we do see errors in our deployment. Now with Istio's retry policies, like I said, they're on by default, but it's still worth taking a look at them. We can specify the types or the number of retries that we can do. We can also specify the type of retry that we do and how long we want to listen for or keep for timeouts and so forth. So now if we apply this, anytime we call the purchase history service, we will attempt to retry 3 times. So let's apply that. And we should, cross our fingers on the bottom, see that the errors go away, because we've implemented automatic retries. Now the last thing that I'll show is that all we did with our application was we added the Istio data plane, right? So we kubectl get pod in the resilience namespace. We see we have our application, but we deployed the Istio data plane, the service proxy next to it. Now the service proxy can do powerful things like routing. It can do things like resilience, like timeouts, retry, circuit breaking, some of which we saw here. But it also can do telemetry collection. And the telemetry collection can be fed back into Prometheus. And then from there, we can open it up in, here. Istio doesn't by default come with these. Oof, all right. 1 second. Latest samples, add-ons. Let's put them there. 1 second. We'll add them there. I should have done this earlier so that we could see all of the telemetry that was collected during our retries and errors that were happening. But that's okay. Let's kubectl. Let's sources Istio. Let's disable the automatic retries again. Didn't seem to disable this time, but nevertheless, let's just take a look at the Grafana dashboard here. The formatting here on Safari doesn't look very good, so let's come over here to Firefox. Now, if we look at our service dashboard, so here's some of the dashboards that come out of the box with this. If we look at our service dashboard, we should see telemetry about the requests that are happening. In this case, we're looking at purchase history. We can take a look at any of them. It would be nice if we can get the errors to come back, but we can see the latency profiles. We can see the number of requests, how quickly requests are coming in, and so forth. So let me stop there. I think I'm running out of time here. There's a lot more to this. I would be happy to if there's interest to come back and give more. But I've run out of my time. If there's, I don't know if there's questions or how we want to handle questions.
Thank you for presentation, for introduction to Istio problems. You covered the problems which this technology trying to solve. Also, thank you for practical insight to the life of DevOps in the matter of connect, secure, control, and observe services in Kubernetes. So if there will be some questions, there should be a question and answers panel, or
okay.
There's also our Slack channel for that. So I will send you an invitation to Slack if there will be some questions about the Istio plugin. Thank you one more again, and I will follow with the second presentation.
Yep, my pleasure. Thank you for having me.